Okay, gang, one more topic, and that is the curl of E. I forgot to tell you we were going to do that video too. So we're going to calculate the curl of E. Remember, we did calculate the divergence of E, but now we got to do the curl. Okay. All right, fine. Let's look at an example, which is the point charge at the origin. Okay, and we know that E for that is just going to be K Q over R squared, R hat, remember, because it's at the origin, so the R prime is 0, okay? So omega is R. Now, we probably know just by thinking about what a point charge, what the E field for a point charge looks like, right? It's kind of this prickly porcupine thing. And it certainly doesn't look like it has any curl, any swirl of the vectors around, right? And so we probably already can guess that the curl of E is probably 0, but let's prove it. Okay, so we know that by Stokes' law, so let's get Stokes' law, the integral of a vector field, well, let's actually just use E, we might as well. The integral over a closed path of E dot dl is going to be the integral over the surface that path bounds, right, of the curl of the vector field. It's just Stokes' law, okay, dotted in with dA, okay. All right, so let's look at the integral of E dot dl for a path, and let's start with not a closed path. Let's just start with a regular path. So I'm going to draw a little coordinate system over here. So we have a little coordinate system here. We have our point charge at the center here. And let's have a path that is, we come out to, we have a point out here A, let's say, and then a point up here B. And we're going to go from A to B. So of course we have a position vector out here, RA, and then we have a position vector out to here, RB, and we're going along some path, whatever path, right? Okay. All right, so we're going along a path here from A to B in our path integral. Okay, so we're going to calculate the integral of E dot dl, and let's figure out along the path that we're showing here, P. Okay. Now, and of course it's going from A to B along that path, A to B. Okay. Now, what's dl? Well, in general, we're going to use spherical coordinates just because this guy is in spherical coordinates, right, with that r hat. So let's use this in spherical coordinates, and remember that's that was that dl in the r direction r hat plus dl in the theta direction theta hat plus dl in the phi direction phi hat, and of course this is just going to be dr r hat plus r d theta theta hat plus r sine theta d phi in the phi hat direction. Okay, cool. Now E dot dl, because this is an r hat and this is an r hat, none of these other things contribute. So E dot dl, so the integral here, we'll do it again, AB, E dot dl is just going to be K, lobbing the K and the Q out, the integral over dr over r squared, because you get the r squared from the E, you get the dr here. The r hats go away because it's a dot product. Okay, fine, and this is really RA to RB, right? Because that's where those points are. And then, so this is going to be KQ, oops, hello, Q, not G, minus Q, oh, I'm doing it again, let me mess that up, let me stop messing up here. So it's going to be K minus 1 over R, that's the integral of 1 over R squared, evaluated between RA and RB. And so this is going to give me K and then Q over RA minus Q over RB. Okay, cool. Now, notice it's path independent, right? Okay, but also if we close the path somehow, right? So if we now take, instead of integrating over this path and just stopping, if we close it on some other path all the way around, right? then the limits of integration are RA to RA. And if I put an RA here and an RA here, I get 0. So this integral over a closed path, A to A, E dot dl, right, is 0. And therefore, this integral is 0, and the only way for them to be 0 equals 0 is if the integrand is 0. So this proves that del cross E equals 0. And this is true for electrostatics where nothing's moving. We're going to have to amend this when things move. But anyway, that's the curl of E. Okay.